Hello, you hear me? Let me see. Yes. Yep. Thank you, Jesus. Hey, welcome to week number 6. So I think we can slow down a little bit. So to do some of the previously unfinished the quiz questions in case you have questions. I think it's a good idea we walk you through some of the solutions and explain it to you. All right, so let's see, we have 35 people. Maybe we can have more. Still got more. Okay. Let me hide my floating. So then I have this one here. So I'm going to walk you through week number 4 quiz B. Okay, I think the quiz A we went through before. So today I'm going to walk you through on this one. And do you guys know what's this? You know that, right? So J equals, interesting. Let me do the red one. J is what? J is 0 plus 1 J, right? So this is 1 e to the power of J pi divided by 2, right? So because E J theta, according to Euler's formula, is what? It's cosine theta plus J sine theta. So you have to know this one, right? So therefore, this one will be like E J pi to the J. So J times J is minus 1, right? J times J is J squared is minus 1. So the whole thing is E minus half pi, right? It's 1 over E half E to the power. All right, so I hope you have no problem on this, right? Do you? Okay. So let's look at this negative resistor. So basically, I hope you will discover that V is some sort of a minus R equivalent, okay, here. So how we can get this one out, okay? Okay, so because this is V as my input, okay, I care about I. So I can put this whole thing as a component, okay? This is my component. So this component, VI relationship, let's check it out, okay? Check it out. So then I write V in terms of I, okay? So we know that, so this is V, so this is V, right? This is also V, right? All right. Okay. So you can see that because this difference here should be epsilon, should be almost 0, right? Because of this amplification, OL is almost infinite, right? It's idealized. So because this is V, so this is V, so this is 0. So basically this is a voltage divider. So here should be 2V, right? So here should also be 2V, right? So 2V divided by R, okay? 2V divided by R is this I, right? And this I plus this I is, so I plus 2V divided by R, right? So this is 2V divided by R is this, this one is 0. So this is KCL at this point, okay? At this point. So therefore, I can write down V equals minus R divided by 2 times I. So this is R0, this is R0. Okay, So therefore, you can see this component, let's say this is component. This component gives us a negative resistance, right? So this is called negative resistor. Possible? Yes, possible. Having an Opamp, we got a lot of things possible, okay? So any question at this point on this? Okay, if you feel like you cannot catch me here about my speed, that's a warning sign. Pretty clear? Okay. Nice, Eddie. Thank you for positive feedback. Okay, thank you. Actually, later you are going to discover positive feedback is bad. It's going to make your system unstable. You need a negative feedback. Okay, so give me negative feedbacks, but in the end, you give the whole course evaluation as positive feedback. That's good. So let's spend some time, relax, don't feel panic. I'll wait you guys pick up. So let's walk through this one. So again, I have something here. I have a current going through here, voltage here. I wrap everything. This is another component, okay? Another component. So I want to find out the VI relationship, okay? VI relationship. So how we should do that. So again, this guy is V, okay? This guy is V, okay? Because this difference here should be epsilon, okay? Should be epsilon, okay? Why? Because this should be epsilon because this OL is so big. No matter what is this one, it's finite. The maximum voltage of this one we have learned is VCC and V negative VCC here. So it's like 15 or 10 watts. So divided by something really big. So this thing is really small. So therefore, this is V, this is also V, okay? So this is also V. Because this is V, I know what is the current in here. So V divided by R. So what is the current in here? Let's say this is I1, okay? Let's say this is IC, okay? This is IC. So what is the IC? So IC is, because I know this voltage is V. Of course, it's V divided by R1, so, okay? But this IC flows through the C, you know that, okay? Flows through the C, so it is also C dVC dt. Is that right? So this assume this is across this one is a VC, okay? VC across the capacitor is a VC, okay? So is this one minus this one is VC. So basically this is if this point is VO. So what is VO? VC equals what? VO minus V. Do you agree? Across the VC, right? So it's a VO minus V is my VC. Okay. All right. So then I'm going to write down, this is dVC dt. So that will be C dV0 dt minus C dV dt, right? Okay. C dV dt. Okay. This is my IC. Okay. This is my IC. So I basically want to find out what is my V0, okay? What is my V0? So I move this guy this side, okay? So I'm going to have what? I'm going to have a V divided by R plus dVt, C dV dt, okay? C dV dt is what? On this side, so it's a C dV0 dt, okay? dV0 dt. Okay. So this is my first equation. I established how to express my V in terms of V0 and V relationship. So let's walk this one through again. So IC, okay, is V divided by R1, okay? So which is C dVc dt, while Vc is V0 minus V, okay? This one, put it here, I have everything here. So this is equation 1. On the other hand, okay, so I have V0 divided by R1 equals V0 divided by R1 equals minus I, okay? Because it should be a KCl, so it should be this one. Should be I plus this one here should be 0, right? Because there's no current flow inside there, okay? Okay, so this is a KCl at this point. So this should be 0, right? Because this is 0, I already can write this thing equals minus I, right? Minus I. Or we can say this is I, this is a minus, okay? Either way, right? Either way. Okay, either way. So do you see everything is correct? Yeah, everything is correct so far. So this is my equation number 2. Okay, equation number 2. So what I need to do is to eliminate my intermediate variable V0. I don't need this one. Okay, I don't need this one. Okay, I don't need this one. So this is my V. So what I have here is if I do d dt both sides, so I'm going to have what? C dv, so this is R1, this is a di divided by dt, okay? So because this one, you do d dt both sides, you're going to have this one, right? But you have a minus sign here, don't forget, minus sign here. You get it? Okay, so good. Let me see. So let me see here. So non-inverting KCl, non-inverting, so I, V0 minus V divided by R1 is 0. So basically we are doing here, okay? We are doing here, okay? This is equation 2, right? Oh, sorry. So this is V0 minus V minus V. So V0 minus V, here you got a V. V0 minus V is Vi, okay? So I'm wrong. Okay, so I was looking at this one. So then that means I have di dt. So you have a so let me write it clearly. So dv0 dt, okay, dv0 dt, you will be the size. So it will be minus I r1 di dt. So this side, so this is a minus sign here. Then I have positive sign here. Okay, then dv dt. Okay, dv dt. Okay, dv dt. But interestingly, so I have one more term which is dv dt. Okay, it's dv dt. Okay, dv dt. So interestingly, because it's c times dv dt, you also have c dv dt. So this term is going to be cancelled out. So what's left over here is v divided by r equals, okay, so I have a minus, okay, c r1, okay, minus CR1 and di dt, okay? So then I can write something like minus CRR1, okay, and di dt. So do you remember what is a component that gives you V equals, usually you have, if you have a L di dt, okay? So this is inductor, right? Inductor. So the inductor value is minus. So it's actually a negative inductor. So this is a minus CRR1. CRR1, okay? Let me see if everything is correct. V divided by, sorry, this is a V divided by R and C dV dt. Yes, yeah, it's correct. It's correct. So that will give you actually a negative inductance, okay? Negative inductance. So you can write this V is L di dt like this way. So this is actually a negative impedance converter. So in other words, if you only have Opamp and a capacitor, but you want actually an inductor, you don't have to buy an inductor, okay? You don't have to buy an inductor, okay? You don't have to buy an inductor. You just use this kind of conversion, okay? Called negative inductance, okay? This is a negative inductance. All right, so questions. I know here you have a little bit detour here. So we did this one is equation number 2. So number 2. Then this one is 0 minus V divided by R. 0 minus V, 0 minus, so this minus R, and you have C, V0 minus V. So you have a current in here, you have current in here, add together is 0. Then you show. So it's the same thing we applied here, okay, by eliminating this dV, okay, this dV dt, we can remove that. So good. So that's our quiz number. Please, if you feel this is still confusing, please work on it. So that's our quiz B. How about our quiz A? Actually, we have quiz A, which is much easier. So I don't think we need to do this. Do you guys know how to say it here? What's this? Which stands for what? Called first order plus delay time. Okay, that's delay time. And I did this one on the class. So this is non-minimum phase, okay, non-minimum phase 0, which will result in undershoot, right? Undershoot. So it defined as what? On the right half plane zeros, okay? So this is a CUPI, right? So the degree of this one is what? Because the numerator in here, maximum order is 2. This maximum order is 2. 2 minus 2. So basically, this is usually in the future, I'll write this is A polynomial S, B polynomial S, then the degree of B minus degree of A is relative degree, okay? Relative degree. For example, what is the relative degree of this one? This is 1. What is the relative degree of this one? Is 2, all right? What is a relative degree of S plus 2? This will be, again, this is 1. This is 2 minus 1, okay? Okay, but let me do one more thing here. say for example, you have s plus 1, you have s plus 2, so you have s plus 3, you have s plus 5. So you have a system like this. So you want to have an input is a step. Step is also called what? Heaviside function. Heaviside function. Heaviside function. Okay, heaviside function. So what is a step output, step response, y of t? Okay, what is y of t? Okay, so you can solve that. Okay, you can solve that by using CUPI. But without solving, I want you to tell me what is y0? What is y infinity? What is that? Can you tell me? So in this case, you need to use what? You need to use initial value theorem. Okay, if you want to do initial value theorem, you need to send s to infinity. Then you limit that. You s times the whole thing. Okay, y of s. What is y of s? It's the whole transfer function times 1 of s. So that's y of s is input. So this is s plus 1, s plus 2, s plus 3, s plus 5. Okay, so you cancel out this s. So what is this one? What is this one? So you divide it by s squared both sides. So you go to 1 plus 0, 1 plus 0, 1 plus, so it's the same, right? 1 plus 0, 1 plus 0, when s goes to infinity. So you have a 1 plus 1 over s, 1 plus 1 over s. So then the whole thing is 1, okay, it's 1. So what is the y infinity? What's the y infinity? You can do the same trick, but you need to, at this time, you need to send s to 0. You still have a s times this whole thing. Then send s to 0, then what do you have? So you have 1 times 2 divided by 3 times 5. So it is something like 2 over 15. That's y infinite, okay, y infinite. So if you draw, this is t, so this is y, so this is y of t. So then you start from here is 1, okay, start from here. Then you end up something very small here. So it's something like this, okay? Initially you are here, this is 0. Infinity, you'll get this is 2 divided by 15. So, but what's inside here? So this is actually called transient. And y infinity and y0, one is called initial value. Another one is called final value. So giving the transfer function and using Laplace transform, IVT, FVT, initial value theorem, final value theorem, you'll be able to get this quickly. But what's really inside here, you need to get is transient. Okay, so this is transient. Transient, okay? So this one, when t goes to infinity, is called a steady state. It's kind of steady, okay? Steady. But how to solve this transient, okay? So basically, I have y of s. I want to do inverse y of s, okay? But I do know that I have 3 poles in here. One is this. Can you color? One, no. Wait a minute. How can I change my pen color? Interesting. I cannot do it. I don't know how to do it.
You can go to the Draw tab on top.
This one? This is not going to help me.
No, where it says Draw.
Oh, this one? Oh, yeah. You're smart. I'm learning from you. I feel happy. So Yes, you're right. Yes. Draw. Yes. So I want to get this one like Laplace inverse of 1 of s, s plus 1, s plus 2, s plus 3, s plus 5. So you have 3 poles, 0, -3, and then -5, right? Okay. Thank you. Thank you. So what you do here is a step that you should practice. Okay. It's called partial fraction expansion. Okay. So basically you write this thing into something like different things like K1 of S plus K2 S plus 3 and plus K3 S plus 5. So how to get K1, K2, K3 quickly, such that if I know K1, K2, K3, then I can use lookup table to write down all this very easily. So this is K1 plus K2 E minus 3t plus K3 E minus 5t. So when t greater than 0, okay? So this is why my y of t. But now the key point is how to get this K1, K2, K3. So of course you can do a common denominator. Then you have the same common denominator here. Then you compare the coefficients of s cubed, s squared, s and s1, s0 constant term. So you get the equation, 3 simultaneous equations. Solve that. That's tedious. It's not going to. If you have 3, you still can do manually. But if you have 10, it's difficult to do manually, right? So we want to tell you we have a trick here. It's called CUPI, okay? So CUPI. So cover up and plug in all these roots, okay? So let us cover up this guy. So I plug in what? Plug in 0. So you have 0 in here. So I know that K1 will be 2 divided by 15. Okay. So this is simple. So now let me do this. So one of us will keep it here. Now I'm going to cover up this guy. Cover up. Then plug in -3. So this will give me 1 divided by -3. Then you have -3 plus 1 is -2. -3 plus 2 is -1. Then I have -3. So this is a +2. -3 plus 5, this is a +2. So then I know that this is a negative. So negative. So this is a -1 divided by 3. Okay. All right. So then let's so let's cover this guy up. I'm plugging -5. I'm going to do 1 minus 5 times. Really, give me a second. Then you have a -5 plus 1 is -4. Okay. Then you have a -4 plus 2 is -2. Oh, sorry. -5 plus 2 is -3. Okay. So then you have -5 plus 3 is -2. What do you get is 2. So it's positive first. Positive, then you have a 2 is 6 divided by 5. So it's a +6 divided by 5. 6 divided by 5. So K1 is 2. So this is 2 over 5, 15. So this is a -1/3. This is 6 divided by 5. So you can see this is so simple now. So when you do CUPI, okay, step response. If I want you to do this, you should be able to do, okay? And so of course, in practice, what if you have this is called a multiplicity. What if you have square? So you can have to the power of n. how you guys going to do it. So that kind of CUPI still applies. Go and check this homework question. There is something like that. They tell you how to do it. So I don't have time to explain to you, but there's another procedure to consider when the multiplicity is not 1, it's 2. In the final exam, I will never do anything higher than 2, okay? But you need to go and find out the ways when it is multiplicity is 2. Go and find a way to do it, okay? But let me do one thing for you. So here, say for example, you have s plus 1 square, okay? So how you can do this? So this is already in a very nice form, okay? So what is the Laplace inverse transform of this one? Okay, inverse Laplace transform, okay? So this actually is a e to the power of minus e. But here, you should have another t. Should have another t. So, okay. All right. So if you say, oh, I never seen this, sorry, it's in your Laplace transformation table. Let me show you. Not this one. So you can see our homework for week 6 is 44 pages, okay? 44 pages. Don't feel surprised. I'll give you, this is called Laplace transformation table. I want to point this one to you. So you said, oh, I never seen that. Now you see it. Oh, okay, wait. Comment. So now you see it. So you can see that when you have this 1 of s, so that is what? Heaviside function. So we have square, you have t. If you only write t, then it's wrong. Don't write t alone. You should write t times ut, okay? Because this is like, if you see t and t greater than or equals to 0, then this is okay. It's the same as this one, okay? So you can see they never lose this ut, okay? Can you see that? We just have seen this thing, okay? So I said s plus 1 square will be a Laplace pair of te minus t ut, okay? Should be like this, okay? So you look, the lambda now is a minus 1, okay? So that's why this is minus 1, okay? Minus 1. All right, so if you have a sine t, ut, what is Laplace transformation pair? Omega b is 1, right? Oh no, that is here. So b is 1, okay? So this one will give you s squared plus 1, okay? This also gives you a pretty good idea of you have two poles. One is plus j. This is the real part. This is the imaginary part. So this is minus j, okay? So this is called a complex conjugate pole with multiplicity 1, or multiplicity 1 on the imaginary axis. So this will give you sine t, okay? Times ut, because when everything t less than 0, everything is 0. So basically, it's like you have t in here. So you have sine t, right? Keep going. But you have something in here like this. But you don't consider that. So you only have something here. Okay. So this is all 0 when it's less than 0. So all 0, then you have this one, sinusoid t, right? Okay. So, but if I move this guy here, say for example, I move this guy here. So this is like -1. Here I have a -1, +1 minus j. Okay, so I have basically I shift this pair of complex conjugated pair on imaginary axis. I move towards this one. Okay, what's going to happen? So this is exactly like this one. So in this case, I have s squared plus 2s plus 2. Do you see that? Okay, so this is the same. Okay, so this is the pose here and here. So then you will have something like this. So let me see if I can change my color. Yes, I can. I'm going to use this one. So you can see that I am going to have something like a sinusoid. It's like I'm dying out. My magnitude is going down. So this going down is e minus t. It's called damping exponential. Damping of the sinusoid with damping. So you have something here. Damping sinusoid. So when you move the pole towards left, so you have more damping. Okay, more damping. So if you just stay on the imaginary axis, you will have sustaining sinusoid. The amplitude will not going up or not going down, not divergent, not convergent. Okay, so you can imagine if you put it here, so then you have something blow up. Okay, the sinusoid. And let me do another color. The sinusoid will have something. So blow up, you have blow up, okay? So that's a question of stability. So you can see that if your poles located in here, so everything will be damped because there's a e to the power of t here. But what if you have something on the right hand side, then it will blow up. So in simple words, you just check where your pole is located, then you will know whether the system is stable or not stable. Okay. So for the sinusoid on the imaginary axis, okay, on the imaginary axis, it is neither blow up nor die out. So it's a sustaining sinusoid. We call this critically stable. It's critically stable. So it's in between stable and unstable. It's critically stable. Okay, critically stable. Okay, interesting. So this table will give you quite interesting examples here. Okay. Another idea is you probably haven't seen this, but if you have so basically if I have output y of t, I hope this will die out so that whatever this will be less than infinity. So if go to infinity is blow out. So how to avoid this one? Okay, how to avoid this one? So there is a very interesting thing I want to draw your attention. So if you have s squared plus 1, okay, so you know this is sine t, right? Sine t, okay? You know this is sine t. But what if you have a square? Okay, then you are going to have something different because of this square. I think this is actually linked to something here. So if you have a square in here, you are going to have an additional t inside here, which is also true. That you end up with something with this t here. So this t here. Okay. So this will give us a trouble. This will give us trouble. That means when t goes to infinity, while sine t is between +1 or -1, okay? So the whole thing will blow up. So in other words, if you have, so in this case, okay, so your poles are still on here and here, but you have a multiplicity here. So I'm going to write this way. So you have a multiplicity 2 in here. So if you have any multiplicity in here, your system will be unstable like this. But it may not be exponentially unstable, blow up exponentially, but it's blow up linearly, okay? Blow up linearly. But if you say you have a triple, you have 3 here, then you have t squared in here, okay? All right, so I think we have done this part, and now it's something we need to review about our quiz of today. No, today of last time, so quiz B. So this is something I want you to be careful, okay? So delayed input, this is my, learn something new, thank you. So this guy is called Heaviside function, but it delayed. So if you have something here, this red one is called UT, right? So this black one is called C times UT, okay, by the way. So this is C, okay? Constant. So then this is shift, okay? It's a delay, okay? It's a delay. So the Laplace transformation of this one is what? It's a C, okay? And it's a constant. If no delay, if there is a delay, it's minus BS, okay? Minus BS, okay? But you may say, how come you can remember this? Sorry, you have to. You have to. So first of all, you have a constant. Then you have a delay. That delay is actually we have another. So actually, this is the table here. So you should have another. So you can see that if you have a delay in S in here, so it will be like this, S minus S0, okay? Okay. This is a frequency shift, okay? This is exponential here. But if you have a delay in here, where is the delay? Yeah, if you have a delay in here, time shift. So we're talking about this one. So then you have this one, okay? So you can see these two, we have some symmetry, okay? You have symmetry. So if you, this is like exponentially weighted function, okay? Then you will have a corresponding Laplace transformation pair. Remember, F and F is a Laplace transformation pair, okay? So this is So what we are talking about, f of s is 1 of s, okay? So our ft here is CUT, okay? So f of s is c divided by s. So this is this part. Okay. Then this is because of this delay. We'll give you this part, okay? Perfect. Yeah, nice. So we just shift that. Now we are going to do something interesting. So we have original f, then minus this guy. So then the overlapping here, it will be cancelled out to 0, okay? So then what's left is a kind of a gate function. So this is a gate function, okay? Gate function. So by that, we know the first one is c of s minus c of s e minus bs. So it is c divided by s, then 1 minus e minus bs. Make sense? Okay. So I'm tricking you here. Okay, I'm tricking you here. So now you have sinusoid, right? So you remember your sinusoid is what? The sinusoid is sine t, sine omega t will give you 1 over s squared plus omega squared. Okay, so that's if it's omega is 1, and then omega, you put it to 1. So now we are doing this. What is the omega? So I know that this is supposed to be what? So this is time t. T is so it's something like that. Let's do this. According to the definition, omega is 2 pi f, while f is 1 over t. Okay, 1 over t. So basically it's 2 pi divided by t. So then t is my period, okay? T is my period. T will be 2 pi divided by omega, right? 2 pi divided by omega, right? T is 2 pi. So here, this is basically is half of the t. So the half of the t is what? Half of the t is pi divided by omega. So this is actually pi, this is omega. So then the whole thing can be written as sine omega t. So basically I have this omega here, okay? P is pi, okay? So Laplace for the transform of that one, if we follow the gate like this, so I simply say, but before we do that, I simply say, because sinusoid, this is a Laplace transformation pair, right? Laplace transformation pair. But remember, you also need to put the omega in here. So let's go and write from here. So this is sine omega. Omega is b, so you need the omega. You need a b in here, right? So, okay. Gotcha. Okay. So I put it in here. So because this is like sine omega t times this gate, okay, times this gate, because this is like a gate function, okay, the gate function. Sine omega times gate. So I'm writing this is my sinusoid, okay, this is my sinusoid, but then this is my gate. So like this one. And unfortunately, this is wrong, okay? So the correct answer is actually plus, okay? Correct answer here is plus, sorry. Okay, but why? Why? What happened? What's wrong? Okay, now we are going to do this type of thing here. So why this is wrong is because you are misled by equation here. Okay. So this is not wrong. This is correct. Okay. So if you write sine omega t ut minus sine omega t ut minus pi divided by omega. Okay. This is a half t. Okay. This is a half the period. Half period. We only have a half period in here, right? Half period. So yes, the Laplace transform of this guy is equivalent to omega s squared plus omega squared, which is okay. This is this term, okay, which is correct. But if you write here, you have your sine omega t by this one, you cannot. You have to write. Listen carefully, okay, please. You don't want to make this problem in your final exam. So you have sine omega t. You should do that. Omega t minus pi divided by omega. Okay? Because this is t minus tau. This is a delay. This is a delay, right? You also do the sine this delay. Then u t pi omega delay, right? Maybe we write this pi. Okay. So we need to write this in this form, but you actually have only t. So what you do is you try to be nice. You add pi divided by omega back. So right. Okay. All right. So all right. So we add minus and add, so it's 0. So it's still like this. So now we are going to do this. So basically I have sine omega t minus pi divided by omega. So this is my angle. This angle, I have omega come over here. I have plus pi. So remember that sine theta, so this is my theta, okay? Plus pi. What's this? Do you know what's this? Sine, cosine, cosine, sine, right? The sine theta cosine pi is minus sine theta, right? Then you cosine theta sine pi. Sine pi is 0. So you only have this one. So this is, do you know that sine alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta? So basically, if you forget this one, it's okay. The sine theta cosine pi is this one. Cosine pi is minus 1. Cosine theta sine pi is 0. So if you say you don't know sine pi is 0, then I cannot help. Okay. So this is a minus. So basically, this one, you simply drop this one. You drop this term by adding a minus sign in front. Oh, I'm sorry. By write a minus sign in front. Okay. And the minus sign, you got positive. Okay. So you got omega sine square plus omega square and e minus pi omega s. So you can see why I have a sign positive in here. It's not negative, it's not minus. It's because I need to write my form is same as this. Let's go back and check it. What's the real formula? Okay. The real formula here is the real formula is, so you now you have this term already, right? I agree that you have this term. You have this term. So this is okay, you have this term. Okay. you have a unit step shifted. But you also need to shift your fx the same way. You can write this way. While originally we are actually writing a x ft u t minus t0. This is not going to work. Okay, be careful. Okay, so in this case, you will really need to go through this Laplace transform and clarify a lot of things here. Okay, so today we are going to spend the rest of the time to go through the Bode plots. Okay, and in our today's quiz, we are going to work on, you will be able to answer this type of question, you answer this type of question. I think in this case, the D is ddt. This is we are using a Heaviside notation, right? You can just replace D with S, okay? So then it's input as output, you circle. So critically stable means your poles are on the imaginary axis. So like I have shown you this one. I also had shown you this one, okay? So you have multiplicity 2 here. Also, you got this as well. So you can see you have this is your so this is your t minus tau. So you y also needs t minus tau. Okay, cannot be t. Cannot be t. Okay, cannot be t. Then you can write this one. Okay, delay. Please be careful. Okay. So, and we are going to do the Bode plots and do a very basic ones. Okay. So let me show you our road mapping here. So we need a Mechatronics. Wait a minute, I need. In our Mechatronics, our roadmap, our Mechatronics roadmap. Okay, so we need the components. Okay, first of all, we talk about Mechatronics synergy. We talked about components. In here, some of you feel stuck. The reason is the idea behind this one, we are going to use KVL, KCL notion. So the generalized of that is linear graph. Okay. So yeah, I think it's good abstraction. And we have a voltage and the current, okay, and generalize this one to a cross variable. Then this is a t variable, okay. Then we made an analogy with R versus resistors, then versus damper, okay. So there's a D type, okay, components. So with that, you should be able to capture all Mechatronics systems to do the modeling part. So it's some practices needed. Okay. So here Mechatronics synergy components, especially in the components, we put more on the Opamps. Okay. So now we are in the signals systems. Then we are going to do controls. Then we're going to do digital controls, okay? Digital controls. So here we need to know two things, but in a nutshell, we need to understand and to understand modeling analysis design, this type of procedure. Not just try and error, not just by your luck. You need a systematic way to do a mechatronic system design. So I think the lab is helping you guys a lot. But still, my job is to pave all the foundations for you. So now, what's lacking in your training probably is the signal and the system part. You basically have time domain and frequency domain, okay? So in the time domain, we already talked about step response. We haven't talked about impulse response. It's basically the same step response, okay? And also we can, so you may ask, what about sinusoids? What about sinusoids? You give me time domain sinusoid input. What is my output? That's a very good question. I think we can delay the start of the body plot the next time, but this is a good idea. It's a good idea to review something usually wrong. Listen carefully, okay? A lot of people make this mistake, okay? So I give you an example I usually give to students. So I have sine t in here to drive my system, which is like 1 plus over s plus 1. This is very simple, right? So what is my yt? Okay, how we do that? We do that. Yes, you can do a lot of things, but if you say, can I try y0 and yt, y infinity? Let's assume that y infinity is limit s goes to infinity, right? So s goes to 0. You have s times, this one is s squared plus 1, okay? So you have s squared plus 1, s plus 1. You send everything to 0. So this s squared is 0, 0. So you put this is 0. This is input. This is output. This is a system. So this is output. So this is y of s. Y of s times s. Send s to 0. Then you get a 0. Do you think this is correct? Unfortunately, this is wrong. And to me, it is insulting. It is offensively wrong, okay, to me, okay? Offensively wrong. Don't do that. Because same thing you cannot apply here. So because your poles of the whole thing are living in not on the left half plane. Because you live on the imaginary axis, and another one is here. Okay, -1 is here. So this is your pole. So you have poles on the right-hand side, or so you are not strictly on the LHP, left half plane, not in here, because you have something on the boundary. That's why you cannot do it. It's not applicable. Only when your poles are in the right half plane, left half plane. Okay. So in this case, you cannot do that. Okay, you cannot do that. In fact, some people may say, "Can you do a sinusoid for me?" So this is as if you say, you have sinusoid. This is a sinusoid, right? So you want to know what is sine infinity. So then you say, oh, s times this one, you send s to 0. This is to 0. Is this to 0? So this is obviously wrong, because sinusoid in the infinity is not decided. It's anything, right? It's absurd, right? Sine infinity, you don't know. Well, what is that? So it will lose meaning in this final value initial value theorem here. Don't apply that for sinusoids. So that's why another reason you have to do this frequency domain response. The correct way to do this frequency domain is, so how to get this YT, okay, get us YT, is to say that you have a Y of t is also sinusoid with the same omega t plus some shift in here, some shift in the phase, and plus you have some magnitude, okay, in the phase, in the magnitude change. While this magnitude will change based on your omega 0. And this is also based on omega 0. So we can plot the theta versus omega, if you have omega changing in here. So then as if I'm seeing if the system is responding, how my frequency changes, then how my magnitude and the phase will change. But remember, it is still a sinusoid of the same frequency in time domain, okay? If you want to do the infinity, it's lose meaning because it's still sinusoid in, sinusoid out, okay? It makes sense to check how its magnitude change, how its phase change. So this is called time domain or frequency domain. So that's why this is called frequency domain response, frequency domain response, okay? We already know how to do step response or even impulse. Impulse, the input, the U of S input is 1 because delta T impulse is 1, okay? So I think everything started to connect all the dots. And so the rest is giving a system in here, okay? Giving a system in here, okay? H of S, okay? H of S. How I can draw y-axis is magnitude in dB, okay, in dB. And log 10 of frequency on x-axis. So this is called Bode plots, okay, Bode plots, okay. And y-axis is in a phase angle in degree, okay, not radians. We don't use radians usually. It could be radians, okay. We don't do that. So at this point, we should understand something called asymptotes, okay, asymptotes. Asymptotic. Asymptotic is because here we put omega. So when omega goes to 0, when omega goes to infinity. So when the frequency is very, very low, the frequency is very, very high, how it changes asymptotically in a limited sense, okay, in a limited sense. So we want to draw that. Remember, I gave you a YT, I gave you T. So because we know what is Y0, what is Y infinity, so I have something in between. So like, going here, starting from here. So you have transient going over here. So this is called asymptotically converged to here as t goes to infinity. And here is asymptotically goes to a constant in here as t goes to 0, as t goes to infinity. So this is called asymptotes. So in frequency domain, we need the kind of concept. So then in the middle, the transient, we hope we will be able to fill up the transient. This is called a Bode plot sketch. Okay, being able to sketch a Bode plot is a basic skill showing that you are no longer a technician. you are engineer. So you basically can show people, not here, okay, not in this time domain, in frequency domain. So then the following is going to teach you how to do that. Okay, how to do that. So I'm going to do that with you next time. So in summary, today we slow down to walk you through a few things we need to summarize. The first is CUPI, okay? Of course, first is our negative resistance, negative capacitance, negative inductance, all these are possible. That's first. Second is, we talked about CUPI, right? We talked about CUPI. We talked about IVT, we talked about FVT, final value theorem. And now let me also remind you here, I also talk about sometimes using IVT, FVT will makes no sense when your input is sinusoid, because you cannot tell what is sine infinity. It is nonsense. So when you have poles in a complex conjugate on here, then you cannot apply initial value, final value theorems, okay? Theorems. We also went through parts of the stability, okay? Stability. So that is shown in today's quiz question. No, it's here. So this is this week's quiz. So I basically will be able to do this. Also, you need to do CUPI, get this analytic formula, okay? So these questions, I hope you can answer. So when you have a complex conjugate pairs on the imaginary axis, so this square will give you t times sine omega t. Okay, the t sine omega t is bounded, so t will go to infinity, so it's unstable. So this case is critically stable, and this case is unstable. Okay, others you can just make your choice. So I'm summarizing up what we have learned today. And I also give you another roadmap point of view, what we are learning, okay? We basically are learning the foundations for mechatronics, okay? And the key part is the modeling, analysis, and design in a systematic way. Then you will be able to draw a line between technician versus engineer, okay? We want you to be engineers, okay? Instead of technician. Okay, so therefore you need to bear with all the math and all this reasonings. Okay, you need to be able to do some sketching. Okay, oh, when t goes to infinity, this goes to this. You know, frequency is very large. It should be like this. So that's why you need to do time domain and the frequency domain. Okay, time domain, frequency domain. So we barely started the frequency domain. I give you motivations. So you cannot, sometimes using time domain, you cannot get insights of the system. So both time domain and frequency domain will be able to help you to understand the system in front of you. So with that, I'm going to stop here. And we are going to continue with the Bode plot and do your quiz. It's become as our tradition. Before midnight, submit it. You are allowed to have 2 mistakes that you missed, then you late. Oh, I forgot, missed the deadline. So you have 2 shots. If you have more than 2 shots, I'll write down your name. Okay. I'll put a note there. So you have 2 mistakes. So it happens, you missed. Okay, I think we can finish here. How can come back? Yes. stop sharing. I know people are saying it's very, two mistakes like late submissions. Okay, yeah. We can forgive you twice, not third time. So I think I slowed down. I hope this will warm you up and have more confidence to move forward. So with that, I'm going to say goodbye to you. We have good showing up, 48, 49. Good, good. Take care and see you on Friday. Okay, bye-bye. Bye, take care.
Wait, Professor.
Bye-bye.
Professor.
Yes.
Oh, you know the two mistakes you're talking about? Does that also apply for labs or no?
Or, not each. Not each. Each, then you have 2 quizzes, 2 homework, 2 lab. No. Totally, you got 2 shots.
Oh, okay.
Don't abuse it. Bye-bye.